Mean time between failure, or MTBF, is a crucial metric for assessing the reliability of electrical equipment, including automatic transfer switches, or ATS. It represents the predicted elapsed time between inherent failures of a system during normal system operation. A higher MTBF indicates greater reliability. The failure rate, conversely, indicates how often a failure is likely to occur. It's typically expressed as failures per a specific time period, such as 100,000 IOs. For contactor-style automatic transfer switches, the mean time between failure typically ranges from 100,000 to 250,000 IOs. This equates to a failure rate of approximately 1 to 10 failures per 100,000 IOs. Circuit breaker-style automatic transfer switches generally exhibit higher reliability. Their mean time between failure typically ranges from 250,000 to 500,000 IOs. This translates to a failure rate of about 0.5 to 2 failures per 100,000 IOs. Several sources provide data and insights into automatic transfer switch reliability, including the Institute of Electrical and Electronics Engineers, or IEEE, Standard 1584.2018, which offers guidance on surge withstand and control of surge currents in low-voltage alternating current power circuits. The National Electrical Code, or NEC, handbook offers guidance and regulations related to electrical installations, which can indirectly impact automatic transfer switch reliability. Manufacturers such as Eaton Corporation, AB, and Schweitzer Engineering Laboratories, or CEL, also provide valuable information. Eaton's Electrical Engineering Reference Guide, ABB Installation Manual for Automatic Transfer Switches, and SEL Application Note 133, titled Automatic Transfer Switch Performance, offer practical insights and recommendations. It is important to note that the mean time between failure and failure rate estimates can vary considerably based on several factors. Firstly, the manufacturer plays a significant role. Different manufacturers may employ different designs, materials, and manufacturing processes, all of which can affect reliability. Secondly, the design of the automatic transfer switch itself is critical. Design features such as the quality of components, the robustness of the mechanical linkages, and the effectiveness of the control system all contribute to overall reliability. Thirdly, operating conditions have a major impact. Factors such as temperature, humidity, and the presence of corrosive substances can accelerate wear and tear and increase the likelihood of failures. Fourthly, maintenance practices are essential. Regular inspection, testing, and preventive maintenance can identify and address potential problems before they lead to failures. The failure rate represents the probability of a failure occurring within a specified time period. It is not a guarantee that a failure will occur at a precise moment. Automatic transfer switch failures can stem from various causes, including mechanical wear, electrical faults, and environmental conditions. Mechanical wear can affect components such as contacts, linkages, and motors. Electrical faults can arise from insulation breakdown, short circuits, or overloads. Environmental conditions can contribute to corrosion, contamination, and overheating. Regular maintenance and testing are crucial for ensuring the reliability of automatic transfer switches and minimizing the risk of failures. Maintenance activities should include visual inspections for signs of damage or wear, electrical testing to verify proper operation, and mechanical checks to ensure smooth movement. Testing should include simulating power outages to verify that the automatic transfer switch transfers the load to the backup power source correctly. Consider these specific aspects regarding automatic transfer switch mean time between failure and failure rates. Firstly, environmental factors significantly influence automatic transfer switch performance. High temperatures, excessive humidity, and corrosive atmospheres can accelerate component degradation and increase failure rates. Implementing appropriate environmental controls such as temperature regulation, humidity control, and air filtration can substantially improve automatic transfer switch reliability. Secondly, load characteristics affect automatic transfer switch lifespan. Frequent switching under heavy loads can induce mechanical stress and electrical wear, reducing mean time between failure. Selecting an automatic transfer switch with adequate capacity and implementing load management strategies can mitigate these effects. Thirdly, maintenance and testing protocols play a pivotal role. Regular inspections, lubrication, contact cleaning, and functional testing can detect and address potential issues before they escalate into failures. Adhering to manufacturer-recommended maintenance schedules and employing qualified personnel are essential for optimal performance. Fourthly, component quality and selection influence automatic transfer switch dependability. Utilizing high-grade components with proven reliability and adhering to stringent quality control measures during manufacturing can enhance mean time between failure. Specifying components that meet or exceed industry standards is crucial for long-term performance. Fifthly, redundancy and backup systems enhance overall reliability. Incorporating redundant automatic transfer switches or backup power sources can provide seamless power transfer in the event of a primary automatic transfer switch failure. Implementing robust redundancy schemes can significantly improve system availability and resilience. Sixthly, surge protection and mitigation strategies are essential. Transient voltage surges caused by lightning strikes, utility switching, or equipment malfunctions can damage automatic transfer switch components and trigger failures. Installing surge protection devices and implementing surge mitigation techniques can safeguard automatic transfer switches from transient overvoltages. Seventhly, monitoring and diagnostics enable proactive maintenance. Implementing monitoring systems that track key automatic transfer switch parameters, such as voltage, current, temperature, and switching frequency, can provide valuable insights into equipment condition. Analyzing this data can facilitate proactive maintenance and prevent potential failures. Eighthly, proper installation and commissioning are crucial for reliable operation. Adhering to manufacturer specifications and industry best practices during installation and commissioning can minimize the risk of premature failures. Ensuring proper alignment, torque, and electrical connections is essential for long-term performance. Ninthly, documentation and record-keeping facilitate effective maintenance. Maintaining detailed records of automatic transfer switch maintenance activities, test results, and repairs can provide valuable insights into equipment performance and trends. This documentation can aid in identifying recurring issues and optimizing maintenance strategies. Tenthly, training and education enhance personnel competence. Providing comprehensive training to personnel responsible for automatic transfer switch operation, maintenance, and troubleshooting can improve their understanding of equipment functionality and potential issues. Skilled personnel are better equipped to identify and address problems before they lead to failures. In conclusion, understanding mean time between failure and failure rates for automatic transfer switches is essential for ensuring power system reliability. By considering factors such as manufacturer, design, operating conditions, and maintenance practices, and by implementing appropriate mitigation strategies, it is possible to optimize automatic transfer switch performance and minimize the risk of failures. Consulting relevant standards, manufacturer guidelines, and industry best practices is crucial for informed decision-making.